So good morning, ladies and gentlemen. So first I introduce me. I am Professor Alain-Luc from Arts et Métiers Paris Tech, and I am working in the Institute of Mechanics and Mechanical Engineering in Bordeaux, in the west-south of France. So I have the pleasure to chair this session. As you know, the discussion is grouped at the end of the session. This is the wish of the organizer, Professor Sedmak, so I have to respect that. Anyway, if somebody finishes presentation sooner, so I mean sooner than 15 minutes, we can ask one or two questions. So I have the pleasure to let the first speaker, Professor Marx, presenting his talk. So you
Thank you very much. Welcome everybody to this presentation. I will show today the results of the PhD thesis of Matthias Thielen, who unfortunately cannot do it by himself, and Professor Motz, as co-author, is the head of our institute. And we have investigated the effect of overloads on fatigue crack propagation, and we have measured this with different techniques, with Barkhausen noise, with digital image correlation, and we have done it with X-ray diffraction and synchrotron. So if we typically investigate fatigue crack propagation, we do this with a constant load amplitude, as you can see here. Our driving force then is the cyclic stress intensity factor. Same cyclic stress intensity factor means same crack propagation rate, and then we get our dA over dN diagram. From the Paris regime, then we can calculate our lifetime. So unfortunately, in real life, our loading cycle is not at constant amplitude. It looks more like this. This is a loading cycle during a bike tour of Matthias. And you see there are some heavy loads under compression and tension. And if you want to describe this, it's quite complex. And so we focused first on just one overload cycle during the fatigue. And what happens then? You would expect that if you have such an overload, this is not good for the fatigue behavior, but it is the opposite way. If you have a look here on the dA over dN diagram, you see that you have retardation in the crack propagation rate up to 1/10 of the crack propagation rate, and this lasts for several, maybe 1,000 cycles up to here to this point where you have the crack propagation rate you had before, and this increases your lifetime, as you can see here. Maybe if 1.5 millimeter crack length would be fracture of your specimen, then you would expect it without the overload after 25,000 cycles, and with the heaviest overload here, in this case 150% overload, you have fracture after more than 125,000 cycles, which is 5 times more than the expected lifetime without the overload. And this is what we investigated now a little bit more in detail. If you have a look in the literature, we will find that the deceleration of the crack propagation rate for different materials, as you can see here, is always in the order between 90 and 95% of the prior crack propagation rate. However, the distance the crack grows through this area of influence is completely different, between several microns up to several millimeters in front of the crack tip, and therefore we investigated this a little bit more in detail. What are the mechanisms which are possible? First, if you have your static crack, you have the plastic zone, and if you have a cyclic crack, you have your cyclic plastic zone in front of the crack tip, which is a little bit smaller than the static plastic zone. And if you have here your applied stress intensity factor calculated just by the stress and the crack length, and the local acting stress intensity factor, which you can measure, for instance, by the crack tip opening displacement, then you will get here a linear behavior. Now, you may have some plasticity-induced crack closure, which means that the crack is closed in the unloading and in the beginning of the loading, and then this will change. You will have your applied K, but you will have the crack opening, the local acting K here at this K opening, and it will change a little bit. And now after the overload, you will have residual stresses in front of your crack tip, and this will change your loading because you will not reach the maximum K, because the maximum stress is now reduced, and therefore it will change your applied K and your local working K in this kind, and this is what we have investigated. We have done we have used three different techniques: magnetic Barkhausen noise, X-ray diffraction in synchrotron, and digital image correlation. Every technique has an advantage or a disadvantage. Here, for instance, we have a very high spatial resolution, and it's quite fast. However, we only see what happens on the surface and not inside the specimen. And with other techniques, we can look at least a little bit inside our specimen to compare it. And here are some details about the material we have investigated. In this case, it was low alloy steel S960 with high strength, and it was a single edge notched tension geometry. Here you see the dimensions. This is just to remember that by the synchrotron measurements we can look inside our specimen by controlling the geometry of the diffraction, and then we can have a look inside the specimen, and then you see that your stresses, this is now the crack tip after the loading, and you see here the compressive residual stresses in front, and it doesn't really change very much, and by the Barkhausen noise you have nearly the same image here, so it's qualitatively at least the same, not quantitatively as you can see here, but qualitatively at least it's the same, and the information is from a depth about 10 microns. But near the surface you have also nearly the same, so what we see with the digital image correlation should also be comparable then with these results. So with the Barkhausen noise and with the synchrotron radiation we can see residual stresses, we can see the stresses during the loading. With the digital image correlation we can only see the strain field between unloaded and loaded specimens. So it's only the strain field after loading. Here you can see the loading. This is a typical fatigue loading up to 1000 newtons in this case. And then we have here our strain field in front of our crack tip. And then we come to the overload. This is a 50% overload. And here we have a 100% overload with a quite huge crack tip opening, and from this we can then also calculate our strain field by the digital image correlation. So now here are the results. This I have shown before. This is the A over the N diagram after the overloads, 50%, 100%, 150%, and these are now the residual stresses measured by the Barkhausen noise before the overload. Here just the compressive stresses from the cyclic plastic zone, and here from the overload zone, and as expected you have an increasing zone with residual stresses with increasing overload. Here now you have the loaded crack tip before the overload, and this is the loaded crack tip after the overload, so it may be somewhere around here, and you see now that your tensile stresses are reduced. Unfortunately now here in this image red means tensile and not compressive as before, so this here are now tensile stresses. So the maximum stress during loading is reduced after the overload due to the residual stresses, and you also find this in the strain field. This here is the crack after the fatigue, and you see the strain field at the fatigue load, and this here is after the overload. You see the crack opening displacement is increased. Here was the overload, and here is a little bit of fatigue crack propagation after the overload, and you have a reduced strain field at the fatigue load, at the normal fatigue load. This might be somewhere here, and if you have a look here at the maximum retardation, you will have only this very small strain field at the crack tip during the maximum load. And then you can also investigate the crack growing through the plastic zone. So this is before the overload, after the overload at position 2, here at position 3, where you have the maximum retardation, the slowest crack propagation rate. The crack tip is still inside the compressive zone, and here at the prior speed, now the crack is still somewhere inside the compressive zone, but the crack also increased, and therefore here you would expect typically for this delta K a crack propagation rate up to here, so you still have an influence even if you are here now at the same speed as you have been here before, but with an increased crack length and therefore an increased applied delta K at least. So now you can also make a quantitative or more or less quantitative analysis of your stress field here in this direction, and then you will see that your compressive stresses, your residual stresses you have here correspond very well with the crack propagation rate you find in your experiment when the crack is growing through this plastic zone and through this residual stress area in front of your crack tip. Now, what are the mechanisms? Remember again this transparency where you have here your applied K and the local working K, and now we have investigated this to see if we have plasticity-induced crack closure after the overload or if it are the residual stresses. And therefore we measured now the crack tip opening displacement, and this here is before the overload in black, and immediately after the overload you see nearly no influence. So at the beginning, after the overload, there's sometimes even an acceleration of the crack propagation rate, but it's only for a very short time, and then it decelerates up to the minimum crack propagation rate. And this is immediately after the overload. You see nearly no influence. You have here this part where the crack is more or less closed, and then the crack opens. So this here is the part, if you remember here, on the plasticity-induced crack closure as you had it before. And this is at the position of the maximum retardation. Then you see you have only a slight increase of the opening K, but you have a huge difference between the maximum opening here in this case before the overload and here for the crack tip opening at the after the overload at the position of the maximum retardation, which corresponds to this diagram, which means that here we have residual stresses because the maximum load is not applied at the crack tip due to the residual compressive stresses. So here we have now our measurements from the synchrotron. It's the loaded crack tip at this position before the overload and the loaded crack tip at this position after the overload. And you see that the maximum load in front of the crack tip is reduced, as you also would expect it if you have to take into account also the residual stresses working after the overload. And now you can do this not only comparing the unloaded and the loaded specimen, you can do it for different positions in your loading cycle, for the beginning loading, mean value of the loading, and also for the maximum amplitude. And then you will get here these results by the synchrotron measurements of your applied stresses. So this is before the overload. There is, with the unloaded crack, nearly no residual stresses in front, and then you start with your tensile stresses when you start with the loading as expected, and here you have your maximum load. And now after the overload at the position of the maximum retardation, you have here compressive stresses. So deep dark blue means compressive stresses in front of your crack tip, and then it starts here with the loading, and when you're here then you are more or less in the area where you have a more unloaded crack tip, and then the crack tip loading starts and you have your reduced loading here in front of your crack tip. And now you can also subtract the residual stresses from the applied stresses, which means the following images are these 4 images minus the values of this image. And then you see that at the beginning of your loading, you have some loading here, you have you have tensile stresses, but they are not working due to the compressive stresses of your residual stresses in front. So what we think that is working is that we, if you have a look here, we would expect plasticity-induced crack closure or residual stresses. We find that we have an influence, that we have not an influence on the opening delta K, but we have a strong influence on the maximum delta K and a strong influence on the plastic zone, and therefore we think it's our residual stresses that are working here for the retardation, and then it takes some time that plasticity induced crack closure comes again into account. And what's very interesting also, maybe as a last result, if you compare different loading ratios, 0.5 and 0, then you will find this effect that you have with 0.5 as loading ratio, you have a stronger deceleration of your crack propagation rate than with the load ratio of R equals 0. And if you make now an experiment which makes just one unloading, so you have here the diagram for the R ratio of 0.5, and this is also for an R ratio of 0.5, but just one cycle with an unloading up to 0 load, then you will get a completely different behavior. So just one relaxation means that you get a different, completely different behavior. And this makes it worth to investigate this further, because your real loading will be very complex, and therefore to describe a real loading cycle will not be so easy. So that's the end of the talk. I thank the Deutsche Forschungsgemeinschaft for if I have the time. Then the conclusion, we have shown that our different techniques can measure the residual stresses, and we also found some kinds of the plasticity-induced crack closure, but obviously the residual stresses are responsible for the deceleration of the crack propagation rate, and then the plasticity-induced crack closure is rearranged when the crack is growing through the plastic zone. And very important is also this relaxation process of the residual stresses during a single unloading cycle, and this is very important for the loading history effect and to describe real loadings as you find they then for real components. So, but then I finish with thanking the Deutsche Forschungsgemeinschaft for the funding, the Fraunhofer Institute for the Barkhausen noise measurements, and the Eddy beamline team for the synchrotron measurements.